All right, let's start lecture B by just doing a quick review of the differential equation example from lecture A. Again, I'm trying to mix in the applications with the content from the book. So the chapter 7 is the main content, but we've also got stuff from chapter 11. That's the differential equations. And ultimately also chapter 8 some this week, as well as stuff with parametric curves. My goal here was to get a solution that looks like this, to find a function whose graph looks like this. And not just any old function, but in a somewhat scientific way. One that satisfies this differential equation that has approximately exponential growth when p is close to 0. Effectively, when p is close to 0, this becomes like a 5, and you get a 5 kp. Approximately exponential growth initially. But then as p gets closer to 5, 1,000 rabbits in this case, this term gets close to 0. The whole thing on the right gets close to 0. The derivative levels off towards 0. The slope levels off, I should say. And then it's a matter of finding a function that satisfies that differential equation. So you separate the variables. You get the p's on the left side and the t's on the right. In this case, the right-hand side is easy to integrate, but the left-hand side is easier. We're illustrating as an application of the method of partial fractions. You do have this type of partial fraction problem on the gateway, so you need to make sure you can do that kind of thing, and especially deal with that minus sign there by putting a minus sign here after you integrate. Then it's a matter of doing algebra to solve for p as a function of t. It was kind of complicated here. If I put this on the exam one, I'd probably have to give you some help to avoid mistakes, perhaps. There's p as a function of time for a general c. It's called a general solution. If you have an initial condition like 0.1 representing 100 rabbits, you can solve for c, plug it in there like I did, and indeed it had a graph that looked the way that I hoped. I plugged in c equals 1 over 49. It was 5c up on top. There was a c here. I picked k equals 0.02. I could have picked something else. I picked, for example, 0.05. It'll still have the same kind of shape. Just increases faster. Okay. Different k's produce slightly different graphs. Question back? No? Okay. All right. Back to parametric curves, vectors. Speed and distance traveled. The reason we're talking about this, well, is twofold. Is because it's important in applications if you take physics or multivariable calculus or differential equations for that matter. And ultimately, we're going to see that a lot of these integrals that come up with trying to find the distance traveled can't be done by hand. And you have to use numerical integration to approximate. So it's a nice area where numerical integration can be used. So you've had these Mathematica assignments where you focused on using cosines and sines. I will continue to do that in class here today. Let's leave this up just in case you want to write on the board. So I'm going to define my f of t and g of t here. They're going to tell me how x and y change over time. I'm going to do something a little different than we've done so far. I'm going to make the frequencies and periods of these functions be different. So the period, how long it takes to go through one cycle, for this one is 2 pi over 3, which is going to be close to 2. And for this one is 2 pi over 5, which is going to be, I don't know, between 1 and 2, smaller. It's a faster oscillation, the second one. Why is oscillating faster? The frequency is the reciprocals of those things. 3 over 2 pi for that one, and 5 over 2 pi for that one. This one oscillates faster, so somehow y is going to be changing faster than x does when we make this graph. I make my c of t function. It's a point-valued function. In Mathematica, I have to type it in as a list with curly braces, like that. And now I can use manipulate and parametric plot to plot this. I'm ultimately going to use show as well to show graphs. B is my animation parameter. It will start at 0 or close to 0 and go up to 2 pi. C of t is what's going to get plotted inside parametric plot. I'm also going to use list plot to plot the dot. C of b is what goes in the list plot. T here goes from 0 to b. And I know I'm going very fast in my typing. I'm experienced with Mathematica. I do make mistakes still, but I can usually type this stuff pretty fast. I don't necessarily expect you to follow it all. And if we put a plot range in here, maybe plot range arrow 2, that might be a pretty good window to see it, although we have to do the axes origin thing. Always kind of an annoyance here. Here we go. So this is going to be a graph that's going to oscillate back and forth because of the cosine and sine, but somehow the sine, the y coordinate, is going to oscillate faster than the x coordinate. And because of that, it's not going to be on the unit circle. Watch it here. Whoops, I made a mistake. I do that often with this one. I forgot extra curly braces around the C to B. There's the motion. Down on a circle. Is it clear that y is oscillating faster than x? And there's more up-down motions overall than there are left-right motions. Yeah, I guess you can see that. This kind of figure's got a name. It's called a Lissajous figure. Lissajous is spelled like this. Lissajous. Must be a French name there. Lissajous figure. That's what it's called. Actually, your physics profs can make these kinds of pictures with lasers. It's pretty cool. They have vibrating mirrors that make the lasers make patterns like this. So we have, let me write down the formulas here. X is cosine 3t. Y is sine 5t. Those are parametric equations. This is a parametric curve. There is a motion there. Is it constant speed motion? That's kind of hard to tell, isn't it? Maybe if I slow it down. If you look at that carefully, it slows down where it turns rapidly. That's what kind of slow. Then it speeds up in the more straightaway areas, which kind of makes sense with, like, if you were driving your car like this, you'd have to slow down in the curves, and you could speed up in the straightaways. What is the speed as a function of time? The formula is the same as always. The speed is the square root of x prime of t squared plus y prime of t squared. Screen show up okay on that?
Yeah.
Use black now. The derivative of x with respect to t is negative 3 sine 3t. Got to square that whole thing. The derivative of y with respect to t is 5 cosine 5t. Simplifies a little bit to square root of 9 sine squared 3t plus 25 cos squared 5t. And there's no Pythagorean identity that can help us when our sines and cosines have different frequencies like this. Is it possible to integrate that to get the distance traveled? Just go ahead and type it in there, up top there. Integrate square root. I'll type it in as f prime of t squared plus g prime of t squared since I've already defined those functions. Can it be done? Thinking, 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 thinking. I let this run for a while on my computer and it never, okay, it gave up. Mathematica gave up. It did, it gave up. It said, I don't know. What does that mean? It means, first, what does it not mean? It does not mean there's no antiderivative of this function. There definitely is an antiderivative of this function. In fact, infinitely many, they're like usual. They all differ by constants. However, what it means is you can't find a simple formula for it. There's no elementary formulas that word people use for this kind of thing. But the antiderivative definitely exists. Instead of finding a formula for it, though, we can approximate it. We can approximate the graph of the antiderivative. In fact, I can do that right now in Mathematica. And probably the best way to do it, to create your distance traveled function, I'll call it dist of t, is to use a command called NIntegrate. Capital N, capital I. Numerically integrate is what that means. Approximate the answer. But I'm going to think of it as a function of t. I'm going to have Mathematica do lots of numerical integrations for different times. T and then graph. It's the same function here, except I think I'm going to use a tau instead of a t, because what I'm really doing is I'm defining dist of t to be the integral from 0 to t of the speed as a function of some other variable, call it tau, d tau. Theoretically, that is the distance traveled, the derivative of this by the second fundamental theorem of calculus is the speed with a t in place of a tau. Right? That's differentiating an integral where the variable is in the upper limit of integration. You get this function, except go ahead and use the same variable as you do for dist. But I'm having Mathematica approximate the integrals, not do it symbolically. That's what NIntegrate is doing. I'm not doing it symbolically, I'm doing it numerically. This means tau is going from 0 to t. Those are your limits of integration. This is ultimately a function of t. Let's plot this. I do this in the videos a lot. Distance traveled and the speed, which is this again. And by the way, that is this. I could have copied and pasted that in. As t goes from 0 to 2 pi, and let's make the original function, let's make the distance traveled blue and the derivative, the speed, let's make that be red. It takes a little while to do it because it's doing a lot of numerical integrations, but there we have it. The red graph is the speed, constantly going up and down, speeding up, slowing down, slows down in the sharp corners, speeds up in the straightaways. The blue graph is how far it's gone. That keeps going up, it never goes down. The red, the speed, is the derivative of the blue. The slopes of the blue are always positive, the values of the red are always positive. The blue is the integral of the red. As you add up signed areas, in this case always positive areas, the blue is keeping track of how much area you have. Now it's maybe a little deceiving here with the scale, but for example, the area here, that's almost a trapezoid. Its base is 0.2. This height is 5. This height is approximately 3. The average of the heights is approximately 4. The area of a trapezoid is the base times the average of the heights. Approximately, in this case, 0.2 times 4, which would be 0.8. The value of the blue at t equals 0.2 should be close to 0.8, isn't it? This is 1 there. It's a little less than 1. Close to 0.8. So don't let the scale deceive you. 1 on the the t-axis is that far, and 1 on the vertical axis is that far. The blue is adding up the areas under the red, so to speak. But we had to use numerical integration. Can it be done by hand and with a calculator? Yes, but it's a lot more work. Numerical integration. What are we integrating here again? We are integrating speed, which again was what? The square root of, what was it, 9 sine squared 3t, I think? Is that right? Except I'll use a tau here. Plus 25 cos squared 5 tau. Does that sound right? Write it down. Looks good, okay. So let's call this function f of tau. Let's pick something specific for t to keep it simple. Let's integrate. Let's approximate the distance after 2 units of time. It's the integral from 0 to 2 of f of tau d tau. Let's go ahead and do what you know how to do already. Do a left-hand sum, do a right-hand sum, and average them. You already know how to do that. So, we'll use a delta t of whatever we want. If we're going to do it by hand, we better not go too small. Let's try 0.5. We need values of the function here. I'm going to use Mathematica for that. Speed, I'll go ahead and call it t. Speed of t here is that formula. This is the thing that I'm calling f here. Probably shouldn't call it f. It's the speed. I could call it h or something. Whatever. If I'm going to use numerical integration, it would be good to find the values of that speed at 0, 0.5, 1, 1.5, and 2. I'll call it t like I'm doing here. 0, 0.5, 1, 1.5, and 2. What are the values of the speed? Plug in different values. In fact, I can sort of do it all at once. Like this. And actually, some of those are going to give me exact forms. I want approximations. Yeah, okay. Let me put dots in there. Decimals to always make them always be approximations. So there's my speeds at those times. I'll go ahead and fill that in. 5, whatever, meters per second, centimeters per second. 5.00007, 1.48015, 3.40646, 4.27828. The left-hand sum, I take the left-hand endpoints of each subinterval. Back up the picture there. It's this interval that I'm breaking into pieces of size 0.5, like that. And it's the red graph that I'm integrating. So I'm focused on integrating this up-down thing. I'm not sure how accurate it's going to be because it goes up and down so much here. I have to use a smaller delta t to be sure I'm going to get a lot of accuracy there. The left-hand sum in summation form can be written like this. And in this case is 4. Actually, this should be an n minus 1 here. So you're going to have 4 terms in the sum. Speed at time 0 times delta t. 5 times 0.5. Speed at time 0.5 times delta t. 5.00007 times 0.5. Plus the speed at time 1. 1.48015 times delta t plus the speed at time 1.5, 3.40646 times 0.5. Okay, you probably should get your calculator out and calculate that now. I will proceed to have Mathematica compute it. These are both approximately 2.5, and they add up to approximately 5. That's about 0.75. This is about 1.7. So what are we at here? Between 7 and 8.
Why did you put a 3 on the top of the summation?
Because n was 4 here, we had 4 subintervals, and that's an n minus 1 for a left-hand sum. So she's looking up here and seeing the 3 there. That is 4 terms in the sum. Answer, what did we say, between 7 and 8? 7.44334, did you get that? Okay. That would be your left-hand sum. Your right-hand sum, RHS, symbolically you could write it I goes from 1 to n instead of 0 to n minus 1. And it would be the same numbers in the middle, so to speak. We would not include the first one. We would include all these. And we'd also include the last value, 4.27828 times 0.5. That is a bit smaller than 5, so our answer for the right-hand sum is going to be a bit smaller than the left-hand sum. You should get 7.08248. If you try that on your own. The trapezoid method, trapezoid rule, you may have heard about. There is a formula for it that doesn't involve the left and right hand sums, but if you happen to know the left and right hand sums, you can just average them, and that's the trapezoid method, and you've done that before. Average these two numbers now. You'll get a number halfway between them, 7.26291. Is that guaranteed to be better than both of the left and right hand sums? Actually, it's only guaranteed, so far at least for us, in the case where the function is strictly increasing or strictly decreasing. This function goes up and down. There's actually no ironclad guarantee for us that this is going to be better than the left and right hand sums. What did NIntegrate do with it? What is dist of 2? If I had to guess, I would say it's closer to that one than the other two, but I don't know for sure. It's not, okay? I can barely see it there. 8.06982. The trapezoid one's not better than the left and right. Well, it's better than one of them. It's better than the right-hand sum was, but it's not, the trapezoid's not better than the left-hand sum for this example. So yeah, that's illustrating that when your function goes up and down, there's actually no guarantee that the trapezoid rule is going to be better. At least for small n, small number of subintervals. If you do a lot of subintervals, probably the trapezoid rule is better. In fact, let's spend the time we have remaining. Well, getting this kind of stuff programmed into Mathematica, then I think we should also talk about vectors. Keep building that. How can you get this kind of stuff programmed into Mathematica, so you can have Mathematica do the summations for you instead of you doing them. Because even with calculator help, they're not pleasant. You can do something like this. LHS, for left-hand sum, as a function of n, the number of subintervals, summation, I goes from 0 to n minus 1 of the speed times delta t. Okay, I'm still doing this one example. I'm still integrating the speed from 0 to 2 to make things as simple as possible. Delta t is really 2 over n. In that case, why? Take your interval from a to b. If you chop it up into n pieces, the length of each piece is b minus a over n. We're integrating from 0 to 2. b minus a is 2 minus 0. 2. 2 over n is what delta t is for our example. Different examples will produce different delta t's. And what do we plug in? On the board I wrote t sub I. What is that? Well, you saw me type it already. It's I times delta t for this example. I times 0.5 is what I did previously. Right there. Why? Well, because when I is 0, that's 0. When I is 1, that's 0.5. When I is 2, that's 1. When I is 3, that's 1.5. I times delta t, when you start at 0 for your left endpoint, is going to be the t sub I that you plug into the function that you're integrating. So in this case, I can write that as I times 2 over n. So this is going to give me, for a general n, a left-hand sum, approximation to the integral. I can do something similar for a right-hand sum. And let me keep them in the same cell, just separate them by a semicolon. You change the L to R. What else do I change? Change the 0 to a 1, change the n minus 1 to an n. That's the right-hand sum. What about the trapezoid sum, the average of the two? I could call it trap. And once I've defined LHS and RHS, I can just use them like this. Now, go ahead and confirm what we got before. When n was 4, what were these things equal to? I'm putting the decimals in to make sure I get numerical approximations. Were those the same answers we got before? It looks like it, yeah. 7.08248, that matches the right-hand sum there. 7.26291, that's the trapezoid sum. And the left-hand one was this. And remember, the more precise answer was dist of 2. I don't need a decimal for that one because I'm doing NIntegrate. It automatically gives it as a decimal. So again, the trapezoid rule in this case was not better than the left-hand rule. It was worse. But if you make n bigger, like 40 instead of 4, 10 times bigger, I bet the trapezoid rule is better with this one, I'm guessing. There's the trapezoid one. That does look like it's the closest to the more precise answer. So the trapezoid rule definitely is better, even with up and down functions, as long as n is large enough. Let's try increasing by a factor of 10 again, see how close we get. Yeah, the trapezoid one is real close now compared to these two. Okay. One of our big goals on Wednesday will be to understand the relationships between the errors of these things. In other words, how close are they to the actual answer? We'll also introduce the midpoint rule and Simpson's rule. Again, on the time we have remaining, hold on, we're not done. Right? Or are we done? Oh, I guess we are. Ah, vectors. I keep having to hold off on vectors. I'm sorry, I was looking at the clock thinking we were done at 12:30. We're not, we're done now. Okay, have a good day.